Welcome to the second screencast on enzymes. This screencast looks at the effects of various factors on the rate of enzyme-controlled reactions. The things we're going to look at in order are pH is going to be the first one. We're then going to look at temperature. We're going to look at enzyme concentration and substrate concentration. Okay, so looking at the first of these, pH to begin with. What does pH mean, first of all? The pH of the solution, as you know, is a measure of its acidity and alkalinity. In terms of what actually pH actually means, it's a scale which measures the hydrogen ion concentration. pH actually stands for minus log to the 10 of the hydrogen ion concentration. So it gives us an indication of the amount of hydrogen ions. Okay, so below 7 we have higher hydrogen ion concentrations, and above 7 we have hydroxide ions, which tend to soak up hydrogen ions. Okay, now for each enzyme, what we find is that there is a relationship between the activity of the enzyme and the pH. So what we find is there will be a particular pH at which the enzyme will have the highest rate of reaction. Okay, and we describe that pH as the optimum pH. For a lot of enzymes in mammals, the optimum pH, particularly of intercellular enzymes, is about 7. However, some other enzymes, such as, for example, pepsin, which is the enzyme that breaks down proteins in the stomach, has an optimum pH of about 2. And that's obviously an adaptation to be able to work optimally in the stomach, which has a high concentration of hydrochloric acid for various reasons. So that's the description of what goes on. So there is an optimum pH for which a particular enzyme works, which is the pH at which that enzyme has the highest rate of reaction. If the pH changes, either gets higher or lower from that optimum pH, what happens is a decrease in the rate of reaction that occurs. Okay? Now, so that's a description of what goes on. If I was to explain why there is that decrease in the activity of the enzyme, either above or below the optimum pH, the answer is that the hydrogen ions, or hydroxide ions in alkaline conditions, they influence two types of bond that we find in the tertiary structure of the protein that makes up that particular enzyme. And the two bonds we're talking about are hydrogen bonds and the ionic bonds. Okay, so we saw the R groups from the amino acids that make up the tertiary structure of the protein, which is what the enzyme is made out of. They can interact with each other via ionic and hydrogen bonds, amongst other types of bonds, as we know. But hydrogen ions, which are very small positively charged protons, can interrupt these bonds, these ionic bonds, and as a result they change the way in which the R groups interact, and therefore the way in which the domains of secondary structure in our protein interact with each other, and therefore the shape. And if the overall three-dimensional shape of the enzyme is changed, there's also a change in the shape of the active site, and if the active site is no longer complementary in shape to the substrate, enzyme substrates cannot form. Okay, so if I look at all that diagrammatically, very simply here, I've got a normal situation as optimum pH where the substrate will be complementary in shape to the active site of the enzyme. We change the pH of the solution, put it in acidic or alkaline conditions, and the hydrogen bonds and ionic bonds in the tertiary structure of this protein get disrupted, and that results in a change in the shape, the tertiary shape, in the three-dimensional shape of this enzyme, and the active site can change shape, and therefore it is no longer complementary in shape to the substrate, and therefore enzyme substrate complexes can't form, and therefore enzyme product complexes can't form, and therefore the product is not produced. What also happens with pH is it can affect the way in which the substrate interacts with the active site. If I use this rather homegrown diagram here, if you have a normal situation at an optimum pH, what can happen is that, let's imagine this red triangle is the substrate and this represents the enzyme, and on optimum pHs that fits very nicely. And what happens when a substrate binds with an active site, there are loose chemical associations that occur between the substrate and the active site. And these may be hydrogen bonds and ionic bonds. Okay, so the positives and negatives are lining up with each other as some sort of ionic bond or hydrogen bond, which are electrostatic attractions between positive charge and negative charge. Now, if you change the pH, so let's say I reduce the pH, which is essentially adding lots of hydrogen ions into the solution in which this enzyme operates, what we find is that the hydrogen ions will start interacting with the negative charges on our enzyme in our active site. Okay, and what will happen then is that what then happens is that the enzyme can't form a bond, partly because, as you can see, it's changed shape, so it doesn't fit in there particularly well. But also what happens is the hydrogen ions are attached to the negative ions in the active site and therefore might repel our substrate. Okay, so those are two reasons why pH can change the activity of a particular enzyme. Okay, so just going back to the top, I'll just quickly go through this slide. So we've talked about what the pH of a solution is. It's a measure of the hydrogen ion concentration. A change in pH causes a change in the hydrogen bonds and ionic bonds, and thus the tertiary structure of an enzyme. Change in tertiary structure causes change in shape of active site. Change in shape of active site equals no enzyme substrate complexes form, therefore no product forms. Okay, so that's a little storyline of what goes on there. Also, hydrogen ions disrupt ionic and hydrogen bonds between substrate and active site, okay, preventing the enzyme substrate complex forming. Okay, and all enzymes have an optimum pH at which is different for different enzymes, as I explained. For example, pepsin has an optimum pH of 2, whereas trypsin, which is another protein digesting enzyme, has an optimum pH of just above 7. What we also find is that minor changes in pH can be reversed. Okay, so if we change the pH back, what happens is the activity comes back. If you have very large changes in pH, what you can do is you can actually denature the enzyme completely, so its activity doesn't return when you return the pH to normal. Okay, so that concludes our little look at the effect of pH on enzyme activity. The second slide is going to look at the effect of temperature on enzyme activity, i.e. the rate of an enzyme controlled reaction. Okay, so we get a graph. If you look here, this is a description of what goes on. So as you can see, as you increase the temperature at low temperatures, what we find is there is an exponential rise in the rate of reaction. Okay, so what that means, for every particular increase in temperature, we get a doubling of the rate. In fact, what we tend to find is for every 10 degrees increase in temperature, we get a doubling in the rate of reaction. Okay, so that's what happens at low temperatures. Okay, and then what happens at high temperatures, we get an optimum temperature at which the rate is at a maximum, and then we increase the temperature above that optimum rate, and then what happens is that we get a rapid decline in the rate of reaction. Okay, so that's a description of what happens at low temperatures. Okay, so at low temperatures there's an exponential rise in the rate of reaction until we reach an optimum temperature at which we get a maximum rate of reaction. At temperatures above that, what we find is the rate of reaction declines dramatically. Okay, so looking at that, an increase in temperature, increased kinetic energy of enzymes, okay, and therefore there's more movement of substrate and enzyme, Okay, and if you get more movement of substrate and enzymes, you're going to get collisions between the two. More collisions, more enzyme substrate complexes forming, and therefore you're going to get more product. Okay, something else you've got to be aware, it says to include reference to the temperature coefficient Q10. What does Q10 mean? Okay, the temperature coefficient Q10, okay, refers to what goes on between about 0 and 40 degrees centigrade, whereas the Q10 is equal to 2. What that means, okay, the Q10 is how, by what factor does the rate of reaction increase every 10 degrees centigrade, and for enzymes it's about 2, so the rate doubles. What it means is it's 2 times for every 10 degrees centigrade, which essentially means that the rate doubles for every 10 degrees centigrade rise in temperature. Okay, that's known as the temperature coefficient Q10. Okay, so then what happens at higher temperatures? The bonds that define the enzyme's tertiary structure are disrupted. Okay, so all the bonds, the hydrogen bonds, ionic bonds, hydrophobic interactions, hydrophilic interactions, etc., start to get disrupted, okay, by the increased vibrations of atoms within the enzyme molecule. That results in a change in the tertiary structure of the protein that makes up the enzyme, and therefore the shape of the active site also alters, and therefore no enzyme substrate complexes form, and therefore no product forms. And at that point we say that the enzyme is denatured. Okay, and at very high temperatures it cannot be renatured, i.e. just cooling the solution down again doesn't bring back the activity of an enzyme. Trying to describe all of that diagrammatically, if I have this situation here, well, this represents some sort of solution, a beaker with a solution in it, and this represents a thing that looks a bit like a kidney bean, represents an enzyme. Okay, so here we've got enzyme with no substrate molecule at low temperatures, and the enzyme moves around because it's got fairly low kinetic energy. It doesn't move around with particular speed. Okay, what I can then do is I add some substrate. So at low temperatures the substrate will also have low kinetic energy and therefore doesn't move around a great deal, and as a result the chance of these two colliding with each other is relatively small. Okay, so that's what happens there. Then if we increase the heat energy, that heat energy gets converted into kinetic energy for both of these molecules which are in solution, so they move around more rapidly, more kinetic energy, and that increases the chance of a collision occurring, and therefore we get a greater rate of reaction. However, at temperatures above that optimum temperature where we get the maximum rate of reaction, what then happens is that the enzyme starts to become denatured and loses its shape. And at that point, even when frequent collisions occur, because these are both moving around very rapidly, okay, but collisions occur, there is no complementary fit between substrate and the active site, and therefore no enzyme substrate complexes form, and therefore the rate of reaction very rapidly declines to 0. So I hope that illustrates the effect of temperature on enzyme activity. Okay, making sure that you can describe what happens at low temperatures and also at high temperatures, but also explain why there's an increase in the rate of reaction at low temperatures and why there's a decrease in the rate of reaction at high temperatures, and also be aware of the idea of the temperature coefficient Q10, i.e. the rate doubles for every 10 degrees centigrade rise at low temperatures from about between 0 and 40, which explains this exponential rise that we experience here. Okay, so that concludes our look at temperature, the effect of temperature on enzyme activity. Our next slide looks at the effect of substrate concentration on an enzyme activity. So substrate, this square brackets around substrate, denotes concentration of substrate. Okay, so what we see here's a graph of the effect of substrate concentration on the rate of reaction. So what we see at low substrate concentrations, what happens is that the rate of reaction increases, but it reaches a rate, a maximum rate, at which further increases in the substrate concentration doesn't result in any further increase in the rate of reaction. Okay, so that's a description. Okay, so at low concentrations an increase until a maximum rate is achieved, beyond which further increases in substrate concentration doesn't result in any further increase in the rate of reaction. Okay, so that's a description. The thing to do is to be able to explain that. Okay, so increasing substrate concentrations. Okay, so this little diagram here shows you we've got some enzymes, okay, and we've got some substrate molecules, and what happens is that they're moving around, and every now and again we get a collision between the substrate and the enzyme, which results in an enzyme substrate complex being formed, enzyme product complex being formed, and then the product being released. Okay. However, if we increase the substrate concentration, so we're going to suddenly look at this portion, what happens is that we have got more substrate molecules, and therefore we're increasing the likelihood of enzyme or substrates colliding with enzymes. Okay, so we've got more. So here we've got two of our enzymes both having had collisions with substrate molecules, whereas at lower concentrations we only had one. Okay, so we've presumably doubled the rate here because we've got two enzymes involved in enzyme substrate complexes, and therefore twice as much product's going to be produced. Okay, and then what happens is if we're keeping adding more and more, okay, we'll eventually get to a stage where all of our enzymes will be involved in enzyme substrate complexes with substrate. Okay, and at that point adding further substrate is not going to increase the amount of enzyme substrate complexes being formed, okay, because the maximum amount of enzyme substrate complexes have been formed. Okay, so adding more substrate is not going to affect. Okay, so the enzyme here, if you like, is the limiting factor. Okay, so quickly going through enzyme substrates. If you increase the concentration of substrate, more collisions between substrate and enzyme, and therefore more enzyme substrate complexes, and therefore more product. Okay. A maximum rate of reaction is reached when all the active sites are bound to substrate, i.e. no more enzyme substrate complexes can form. Now, in all my descriptions of these, I keep using these words enzyme substrate complexes and product being formed and so on. The reason for doing this and talking about words like collisions is if you get a question, there are marks on offer for using this type of language. Okay, so make sure that you include this type of language in any answer to questions that you're asked. Now, if I try to represent that diagrammatically, if you can imagine here, I've got some enzyme molecules in my solution, and if I start to add some substrate, what will happen is that the more substrate I offer, so this will eventually collide with an enzyme and we'll get some product formed. If I have double the amount of substrate, there's twice the likelihood of a collision occurring, and therefore twice the likelihood enzyme substrate complexes forming. And if I keep adding more and more and more, what will happen is a stage will be reached when all of the enzymes are involved in forming enzyme substrate complexes, and therefore there are no more enzyme substrate complexes can form. So adding more molecules at this stage is not going to further increase the rate of reaction. Okay, which explains why we get this characteristic curve, which is sometimes described as saturation dynamics, where we get an increase in the rate at low substrate concentrations, but that reaches a maximum when further increases in substrate concentration doesn't result in any further increase in the reaction rate. Okay, so that looks at the effect of substrate concentration on the rate of an enzyme controlled reaction. So this slide looks at the effect of enzyme concentration, again the square brackets denoting concentration of enzyme. If we increase the enzyme concentration, what happens to the rate of reaction? So at low enzyme concentrations, what we find is that we get an increase in rate, okay, and then what happens is that we end up with a maximum rate occurring, okay, and after that very rapidly the rate drops to 0. Okay, so that's what happens there. If there is a plentiful supply of substrate, if you add more enzyme, you just increase the rate of reaction. Okay, and we'll explain all of that. Okay, so if you add more enzyme, you're going to get more collisions between substrate and enzyme, and therefore more enzyme substrate complexes, and then more product we form. If the substrate is limiting, okay, then what happens is you reach a maximum rate, okay, which is when all the substrate is bound to active site, okay, and then obviously all the substrate then gets converted into product very rapidly, and therefore there'll be no substrate left, and therefore the rate drops to 0 as all the substrate gets used up. Okay. If the substrate's in excess, however, the rate continues to rise. Okay, so if I show you that diagrammatically, what happens, if you can imagine here, I've got a container, a beaker, let's say, with some substrate molecules denoted by these blue blobs. Okay, and the enzymes, if I add some more enzyme, if I add enzyme to these, if I add some enzyme, okay, the rate of reaction will initially be quite low. Okay, so this enzyme move around will eventually collide with these, but it can only collide one at a time, and therefore the rate of reaction is quite low. If I add, however, more enzyme, what I'm going to do, a second enzyme molecule, double the concentration of enzymes, I'm going to have twice the likelihood of a collision occurring, and therefore that will result in twice the rate of reaction. Okay, so going back to that would represent this graph here, where we've got a plentiful supply of these blue blobs, which are the substrate, and therefore adding more enzyme results in just an increase in the rate. Okay. However, if I go back down here and I continue to add my enzyme, okay, so the enzyme, as I add more and more enzyme, what happens is that we continue to increase the rate of reaction as more enzyme substrate complexes form, because there are more enzymes for the substrate to collide with, but it will get to a stage when there's so much enzyme there that we have a maximum amount of enzyme substrate complexes forming, and therefore by adding more enzyme we're not going to actually further increase the rate of reaction, because for these enzymes there is no available substrate for them to bind to. Okay, so they're not going to have any effect on the rate of the reaction. Okay, and at that point what happens is that our maximum rate will be achieved, okay, and then very quickly what happens is that the enzyme will convert all those substrate molecules into products, and therefore there won't be any substrate left, and therefore the rate of reaction will drop to 0 very rapidly thereafter. Okay, so that explains the effect of the enzyme concentration on the rate of an enzyme catalyzed reaction. The last of the slides on this screencast, Enzymes 2, looks at some practical considerations to take into account when measuring the effects of pH, temperature, enzyme concentration and substrate concentration on enzyme activity. Okay, so a few things you might think from the whole way that practicals work. So one thing to think about are the 3 types of variable that you encounter when you do any form of practical. So you would be thinking of the input independent variable, okay, which is sometimes called the input variable, and the dependent variable, which is something to do with the outcome. Okay, so the independent variable will be the thing that you choose to change. Okay, so you might be looking at changing the substrate concentration, and in that case that would be the independent variable, and you'd be then the dependent variable in that particular situation, or the outcome variable, would be the change in the rate of reaction. Okay, so that graph that I showed you earlier, where you get an increase in the rate of reaction until you reach a maximum, okay, that's with an independent variable of the substrate concentration, and the dependent variable the rate of the reaction. Okay, the other thing to think about are the controlled variables. Okay, so when doing an experiment you'd have to think of all the other influences which might be confounding influences on the dependent variable. So temperature would also affect the rate of reaction, so you'd have to make sure that all of your tubes were at the same temperature when you had different substrate concentrations, so that you could eliminate the temperature as having any influence on the rate of reaction. Similarly, you'd want the pH to be constant, and similarly you'd want the enzyme concentration to be constant, okay, because all of those would have an effect on the outcome, i.e. the dependent variable. Okay, so you've got to consider that. In terms of how do we measure rates of these reactions, like any rates of reactions, what we really need to have is some visible thing that we can measure. Okay, a lot of these enzyme reactions will be converting transparent substances into other transparent substances, and therefore they're very difficult to measure the rate at which those reactions occur. However, if there is an enzyme controlled reaction that has some sort of visible outcome, that gives us a way in which we can easily measure the rate of reaction. Okay, so changes of state are a very good example. So if a gas is produced from the liquid phase, that provides us with a very easy way of measuring rate. So the enzyme catalase, which we've mentioned before, which breaks down hydrogen peroxide into water and the gas oxygen, gives us an excellent opportunity to measure the rate of reaction. Okay, so if I had a piece of apparatus like this, where I have I could have some hydrogen peroxide in there, and then what I do is I can introduce some enzyme catalase into this, and then that will result in gas being produced, which I can then collect. I can have a measuring cylinder or a gas syringe, however I want to do it, and I can measure the amount of gas which is produced in a given time. And then if I can increase the temperature, I can see how that affects the amount of gas produced in a given time. I can change the concentration of hydrogen peroxide, I can change the concentration of the enzyme, and so on. So I can do some experiments to find out what the effect of all these input variables or dependent variables are on the rate of the catalytic breakdown of hydrogen peroxide by the enzyme catalase. The other way I can do it is I can measure the rate at which substrate is used up. So in this particular case, what I can use is another enzyme we've come across before, amylase, which breaks down starch. Now, as we know, starch turns iodine a blue-black colour. So what I can do is I can get some of these tiles, which are called spotting tiles, and put iodine in all of these wells in the spotting tile. And then what I can do is I've got some starch and some enzyme. And then what I can do is I've got a reaction vessel, which is, let's say, a test tube, and I put the enzyme, the starch, and the amylase together in a test tube, and then I have a timer, and it's all mixed together. And what I do is every, let's say, 30 seconds, I take a sample out of my reaction vessel and drop it into a well of the spotting tile. So every 30 seconds, and what we'll find is initially there is starch available, but when the starch all gets broken down into maltose, as we can see over here, there's no starch left, and therefore the iodine doesn't turn blue-black. Okay, so I can measure the time which it takes for the starch to disappear. Okay, we can and then repeat that experiment, but do this with different enzyme concentrations or different substrate concentrations or at different temperatures, okay, to see what the impact on those is on the time it takes for our starch to disappear. Okay, the difficult one about this is actually, as you can see, actually judging the endpoint. When has all the starch disappeared? That's a tricky one. But as long as you have the same endpoint for each time you do the experiment, you can get data from which you can draw a graph to work out the effect of either enzyme, substrate, temperature on the rate of an enzyme-controlled reaction. Other ways of doing it. The enzyme lipase, which is another enzyme you came across at GCSE, that breaks down triglycerides, which we've come across in the AS course or the A-level course. It breaks those down into fatty acids, and fatty acids obviously reduce the pH of a solution, so we can monitor this reaction with a pH probe or by using universal indicator, and so on. We can monitor the amount of fatty acids produced by this enzyme lipase on that. To be another way in which we could measure the rate of an enzyme controlled reaction. One of the problems with enzyme assays, as we call them, which are the reactions that we use to measure the rate at which enzymes react, as the enzyme reaction proceeds, the controlled variable, which is very difficult to control, is the substrate concentration, because as the enzyme progresses, the amount of substrate, or the concentration of substrate, reduces. Okay, so it's actually very difficult to control substrate. So if you're, let's say, doing the effect of temperature on an enzyme-controlled reaction, it's very difficult to control the substrate concentration, because as the reaction progresses, the substrate concentration declines. Okay, so what biochemists do is they work out the initial rate of reaction. Okay, so if you take this as an example, we've got a reaction, we've got an independent variable here, and the rate of reaction there. Okay, so what happens is the rate starts off to be quite high, and then it starts to drop off a bit because the substrate level, the amount of substrate starts to be used up. Okay, so what we do is that we draw a line, a tangent from the initial curve up here. So we draw a straight line from the initial curve here. Okay, and we can work out the what we can do is we can work out the rate of reaction from looking at the gradient of this line that we draw here as a gradient of the initial curve there. And that can give us the initial rate of reaction, which is a useful value for biochemists, because we know the initial rate for any reaction is when the amount of substrate is at its maximum amount. Okay, so that's why we often will seek to find out the initial rate of any enzyme-controlled reaction. Anyway, that concludes our look at this little bit about the enzymes. So we've just looked at various practical investigations. You will do a number of practical investigations involving enzymes where you'll encounter some of these ideas.